Fraud alert threshold design. Banks need to detect suspicious transactions. Setting the right alert threshold is critical for minimizing fraud. If the threshold is too low, many legitimate transactions get flagged. If it is too high, fraud may go undetected. In this lesson, you will explore real examples and datasets. You will learn how to create, tune, and validate thresholds for fraud alerts. We will use synthetic banking transactions data to keep it simple and realistic. By the end, you will be able to design your own fraud alert rules in Python. Running the cell now. We import pandas to work with tabular data. We import NumPy for generating synthetic numbers and calculations. We import the warnings module to control warnings. We disable all warnings to keep the notebook output clean and easy to follow. Running the cell now. Understanding the data. Our dataset contains synthetic banking transactions. Each transaction belongs to a customer and includes the transaction amount, type, channel, and timestamp. The key column for this lesson is amount, which we will use to design alert thresholds. Beginners often forget to check for negative or unrealistic transaction values. Watch for missing or duplicated transaction records. Running the cell now. We set the random seed to 42 so our results match every time. We set the random seed for reproducibility. We specify the number of synthetic banking transactions. We select the number of synthetic customers. We generate the transaction records as a pandas data frame. Each transaction gets a unique transaction identifier. Every transaction links to a customer. Amounts are generated using a normal distribution with a mean of 150. We randomly assign each transaction type, debit or credit. We randomly select the channel, ATM, online, branch, or POS. Each transaction receives a timestamp that is 1 hour apart. We display the number of rows and columns in the data frame. We show the first 3 transactions for a quick preview. Running the cell now. This output confirms our synthetic dataset has 1,000 transactions and 6 columns, including the key amounts and relevant identifiers like transaction_ID and customer_ID. The first few rows show varied amounts, transaction types, and channels, illustrating the diversity of data we will analyze. Noticing the realistic timestamp sequence and no obvious negative or missing values helps ensure we start with clean data for setting alert thresholds. Try increasing or decreasing n_transactions and see how it affects the data. If you want more practice, experiment with a mean and standard deviation when generating amounts. Some generated values might be negative, which is not realistic. We remove any transaction with a negative amount. We print the new shape of the data after filtering out invalid transactions. We show summary statistics for the amount column to understand the typical range. Running the cell now. After filtering out negative transaction amounts, we see the dataset now contains 993 transactions with only positive values, which makes the data more realistic for analysis. The summary statistics of the amount column show a reasonable range and distribution, confirming that our data cleaning step is effective and that these values are suitable for setting alert thresholds. This step highlights the importance of validating transaction amounts before further analysis. Why might negative amounts appear in randomly generated data? Think about what negative transactions mean in real banking. Exploring transaction amount distributions. To set a fraud alert threshold, you first need to know what normal transactions look like. Looking at histograms and basic statistics helps you see patterns. Some customers or transaction types may have higher normal amounts. Running the cell now. We import matplotlib.pyplot to visualize the data. We plot a histogram of transaction amounts using 30 bins. We label the x-axis as transaction amount. We label the y-axis as frequency. We set the plot title to show what the chart is about. Grid lines make it easier to compare bar heights. We display the plot. Running the cell now. This histogram shows the distribution of transaction amounts, with most transactions clustered at lower values and a long tail extending to higher amounts. Notice how the frequency bars reveal common transaction sizes, helping us identify what typical behavior looks like before setting fraud thresholds. This visual check is key to distinguishing normal from potentially suspicious transactions. Can you spot any outliers or strange spikes in the transaction amounts? We display the top 5 transactions with the highest amount values to spot potential fraud cases. Running the cell now. Here we identify the top 5 highest transaction amounts to understand the upper range of normal activity. Noticing these values are all around $300 plus helps set a reference point for what could be unusually large and potentially suspicious. This insight supports setting realistic fraud alert thresholds based on actual transaction data. How would you investigate these very large transactions in a real bank? We compute the mean of all transaction amounts. We calculate the standard deviation, which measures spread. We print the calculated mean so we know the typical value. We print the standard deviation for reference. Running the cell now. Here, we calculate the average transaction amount and its variability to understand what typical spending looks like. The mean of about 153 and a standard deviation near 62 suggest most transactions cluster around this range, guiding where we might set thresholds for unusual or potentially fraudulent activity. This foundational insight helps us distinguish normal behavior from outliers in later analysis. Try calculating these for each channel or transaction type for deeper insight. We set an initial rule that flags any transaction above $300. We filter all transactions where the amount is greater than $300. We print how many transactions would be flagged using this threshold. We show the first 3 flagged transactions. Running the cell now. This output shows that 10 transactions exceed the $300 threshold, indicating potential outliers or fraud risks. The sample flagged transactions confirm amounts just above the threshold, helping to validate the choice of $300 as a cutoff. This step is crucial for understanding how many and which transactions might trigger alerts based on the amount distribution. What would happen if you lowered or raised the threshold? We add a new column is_alert that marks true if the transaction is above $300. We count how many transactions are flagged as true or false. Running the cell now. This output shows that setting a fixed fraud alert threshold at 300 flags only 10 transactions as alerts, while 983 are considered normal. The large imbalance highlights that most transactions fall below this amount, helping us understand what typical transaction amounts look like before refining alert thresholds. This simple count is a first step in identifying unusually high transactions within the dataset. A fixed threshold is simple but may not suit all customer types or seasons. We calculate the cutoff for the highest 5% of transaction amounts. We set is_alert_5 PCT to true if the amount is above the 95th percentile. We print the threshold value for the top 5%. We count how many transactions are flagged by this rule. Running the cell now. The output shows the 95th percentile threshold for transaction amounts is about $252, meaning transactions above this are unusually high. Notice that only 50 transactions exceed this limit, indicating the top 5% with potentially risky amounts. This helps set a data-driven alert level by focusing on the highest value transactions. Using percentiles adapts to the data and is often more flexible than a fixed number. We combine 2 conditions: the channel is ATM and the amount is greater than 200. We count and print the number of flagged ATM transactions. Running the cell now. This output shows that 63 ATM transactions exceed the $200 threshold we set to flag potentially unusual activity. Noticing this count helps us understand how many transactions might need closer review when setting fraud alerts. It highlights the importance of choosing a threshold that balances catching suspicious behavior without overwhelming us with too many flags. Try creating similar rules for other channels or transaction types. Intermediate threshold design examples. Some customers do more transactions or bigger transfers. You can design thresholds based on customer history or other features. This helps reduce false alarms for large but normal customers. Running the cell now. We group the data by customer identifier and get the mean amount for each customer. We print the average transaction amounts for the first 5 customers. Running the cell now. Here, we calculate the average transaction amount per customer to capture their typical behavior. Notice how each customer _ID maps to a distinct mean value, reflecting individual spending habits. This step is crucial for designing personalized thresholds that reduce false alarms by accounting for customers who normally make larger transactions. Strong customers may have much higher normal transactions, so one size does not fit all. We calculate the mean and standard deviation for each customer. We merge these stats back into our main data frame so each row knows its customer stats. We flag an alert if the amount goes above 2 standard deviations from that customer's mean. We count how many transactions are flagged under this dynamic rule. Running the cell now. This output shows that only 4 out of 993 transactions are flagged as alerts because they exceed 2 standard deviations above each customer's average transaction amount. Notice the large imbalance between false and true counts, reflecting that the dynamic threshold effectively filters out typical transactions for each customer while highlighting unusually large ones. This demonstrates how customizing thresholds to individual customer behavior helps reduce false alarms from regular but high-volume customers. Dynamic thresholds help personalize fraud detection to the customer's history. We print the number of flags using the fixed rule. We print the number using the customer-adjusted dynamic rule. Running the cell now. This output compares the number of alerts triggered by a fixed threshold versus a dynamic, customer-tailored threshold. Notice that fixed rules generate more alerts, 10, while dynamic rules reduce alerts to 4, demonstrating how personalized thresholds can lower false alarms for customers with varying transaction behaviors. This aligns with the lesson's goal of designing smarter, adaptive alerts based on individual customer history. Which rule flags more transactions? Think about which rule ensures better precision. We make a rule for late night, from 11 p.m. to 5 a.m. We consider a transaction suspicious if it is late night and over $150. We print the number of suspicious transactions happening late at night. Running the cell now. This output shows that 151 transactions occurred late at night with amounts over 150, highlighting potential suspicious activity during off hours. The code uses a time-of-day threshold to flag these transactions, demonstrating how incorporating temporal patterns can refine alerts and reduce false positives for customers who might otherwise seem normal during the day. Notice how this approach helps target unusual behavior specific to certain times rather than blanket rules. Try changing the hour range or amount threshold to adjust sensitivity. We make a complex rule if either dynamic or top 5% is true and transaction is late at night. We count how many transactions this combo rule flags. Running the cell now. This output shows the count of combined alerts where either a dynamic threshold or a 5% alert is triggered during late-night transactions. Notice most rows, 977, are false, meaning the combined rule filters out many transactions, focusing alerts on just 16 cases. This demonstrates how combining multiple criteria can fine-tune alerts, minimizing false positives for customers with high activity while still catching unusual behavior at specific times. Combining rules can reduce false alarms without missing too many true frauds. Subscribe to our YouTube for more Python finance tutorials. Advanced threshold and model-based approaches. Statistical outlier detection, ROC curves, and monitoring false positive rates are advanced tools. More advanced rule tuning uses precision, recall, and cost-benefit analysis. You can compare chosen thresholds for performance using confusion matrices. Running the cell now. We import confusion_matrix and classification_report from Sklern. For practice, we decide that a fraud transaction is anything above $350. We make y_true as the ground truth label. We use our fixed alert as the prediction. We build the confusion matrix to compare them. We print the confusion matrix so we can see true positives and false positives. We print a classification report for precision and recall. Running the cell now. This confusion matrix reveals that the model flagged 10 false positives, non-fraud labeled as fraud, but failed to detect any actual fraud cases, no true positives. Notice how the support for the fraud class is 0, indicating no alerts match the fraud condition, which leads to precision and recall of 0 for fraud detection. This highlights the importance of tuning thresholds and evaluating models beyond accuracy, focusing on balancing false positives and false negatives in outlier detection. How well does our alert threshold detect high-value fraud? For more videos, check our channel for ROC curve and threshold calibration. We import ROC analysis functions from Sklern. We import matplotlib again for plotting. We calculate ROC curve statistics using amount as the score. We compute the area under the ROC curve for evaluation. We create a new figure for plotting. We plot the true positive rate against the false positive rate. The orange line shows the model's performance. We plot a baseline diagonal to represent random guessing. We label the x-axis as false positive rate. We label the y-axis as true positive rate. We title the plot as receiver operating characteristic. We display the legend at the lower right. We show the ROC curve plot. Running the cell now. This ROC curve shows how the true positive rate varies with the false positive rate for different threshold settings on the amount feature, highlighting the trade-off between sensitivity and specificity. Notice the curve bows well above the diagonal line, indicating good classifier performance, with an AUC score quantifying overall accuracy. This visualization helps you select an optimal threshold by balancing detection capability against false alarms, which is key for advanced model tuning. ROC curves help you pick the optimal threshold depending on your business risk. We initialize variables to store our best F1 score and best threshold. We initialize the best threshold value. We import F1_score for model evaluation. We iterate through thresholds from 150 to 400, stepping by $10. We apply each threshold to flag fraud cases. We compute the F1 score for each threshold. If this F1 score beats our previous best, we save it. We update the best threshold when current F1 exceeds the previous best. Finally, we print the best fraud alert threshold by F1 score. We print the value of the best F1 score. Running the cell now. The output shows that the automated threshold optimizer failed to find a meaningful threshold above 150, instead returning 0 with an F1 score of 0. This suggests that the chosen feature or threshold range does not effectively separate classes, highlighting the importance of selecting appropriate thresholds and features in advanced model tuning and the role of performance metrics like F1 in guiding these decisions. Automated search helps quickly find optimal thresholds for any dataset. Error handling and debugging in threshold alerts. Watch out for missing values and non-numeric amounts. Always check for duplicate transaction IDs. Print debug outputs whenever your rule flags a huge or unexpected number of alerts. Running the cell now. We count missing values in all columns to catch data quality issues. We print the sum of missing values for each column. We print a label to clarify what is coming up in the output. We print the missing values by column. Running the cell now. This output shows the count of missing values in each column of the dataset, with only the STD column containing 6 missing entries. In the context of threshold alerts, noticing these missing standard deviation values is crucial since they could affect the calculation of dynamic alert thresholds and potentially lead to errors or missed alerts. This debug step helps ensure data quality before applying alert rules. If you find missing values, consider dropping or imputing them. We look for duplicate transaction identifiers, which should be unique. We count how many duplicates there are. We print the number of duplicate identifiers. Running the cell now. The output shows there are 0 duplicate transaction IDs, indicating each transaction is uniquely identified. This confirms that the dataset is clean in terms of duplicates, which is crucial for accurate threshold alerting and avoiding duplicate alerts in the error handling process. Duplicates are a serious issue for fraud analysis. We add a check for any negative transaction amounts. If any exist, we print a warning. If not, we print a reassuring message. Else block ensures you do not miss unexpected values. We give a clear print for healthy data. Running the cell now. This output confirms that there are no negative values in the amount column, which is crucial for ensuring the reliability of threshold alerts based on transaction amounts. By including this defensive check, the code helps catch invalid data early, preventing false alerts or errors later in the pipeline. Notice how this simple condition acts as a safeguard to maintain data integrity before applying more complex rules. Add similar checks before any rule-based flagging function. Best practices for fraud threshold rules. Always review data before building alert rules. Start with simple fixed thresholds but move toward dynamic ones. Tune thresholds based on business goals and false positive rates. Validate your rules using confusion matrices or ROC analysis. Log alert volumes to spot sudden changes over time. Running the cell now. We extract the date part of the timestamp for log aggregation. We group and sum how many fixed alerts occurred each day. We print the daily alert log for the last few days. Running the cell now. Here, we see a daily log of alert counts showing mostly 0 alerts with a single alert on the last day. This simple time series helps monitor alert volume trends over time, supporting the best practice of logging alerts to quickly spot sudden changes or unusual spikes that might indicate tuning or data issues. Spikes in alert volumes may signal fraud waves or threshold drift. We make a new data frame with transaction ID, amount, date, and customer identifier. We define an alert threshold at $320. We create an alert column based on this threshold. We select only flagged transactions for reporting. We print how many were flagged from the total for this example. We plot a histogram for both flagged and normal amounts for visual clarity. We plot normal transactions as a blue background. We plot flagged transactions as an overlay. We label the x-axis as amount. We label the y-axis as frequency. We title the plot to show the purpose. We add a legend. We display the visualization. Running the cell now. This output shows that using a fixed threshold of 320 flags only 4 out of 993 transactions as alerts, highlighting how strict or lenient the rule is. The overlapping histograms help visualize the distribution of normal versus flagged amounts, emphasizing the separation created by this threshold. This step demonstrates the importance of reviewing data distributions before tuning thresholds to balance alert volume and false positives effectively. Try this workflow from scratch using your own synthetic thresholds. You are ready to make better fraud alerts. Practice tuning thresholds and combining dynamic features. For more banking analytics, visit our YouTube channel. Running the cell now.